Hello everyone. In this video we're going to learn how to multiply and divide radical expressions. In a previous video we learned how to multiply and divide radical expressions containing just one term. In this video we'll learn how to handle when there is more than one term involved. As you recall, we learned these two rules for situations where the nth root of x and the nth root of y are both real numbers. Then we learned that we can multiply under the radical and we can divide under the radical. This is called the product rule for radicals, and this is called the quotient rule for radicals. And we'll be using these rules again in this video. So looking at this first problem on the left, the instructions are all the same. We're going to multiply and simplify. Here, of course, we're going to distribute this -6 into this group, and we end up with -6 radical 32 minus 6 radical 2. Of course, we never leave a problem before we make sure we've fully simplified it. So if we look at the prime factorization of 32, we have 2 that goes into it 16 times, 2 again, 8 times, 2 again, 4 times, 2 times, and 2, 1. And this is only needed in case you're not comfortable with numbers, but there's always a way to handle this. So we notice that there's a perfect fourth power of 2, which we know is 16. So we can break this up as -6 radical 16 times radical 2 minus 6 radical 2. So that's going to be -6 times 4 radical 2 minus 6 radical 2, which is -24 radical 2 minus 6 radical 2. And of course now we have two like terms because the radical parts are the same. So we can go ahead and combine those to get -30 radical 2. Okay, so on this next one, we could go ahead and distribute the square root of 5, but it will be easier if we actually simplify the square root of 54 and the square root of 96 before we do so, because then we'll be dealing with smaller numbers. So let's go ahead and take a look at the prime factorization of 54 and 96 to see what kind of perfect squares they may be hiding within them. So 54, we start with 2, that gives us 27. The next prime is 3, which gives us 9, and then 3 again gives us 3. One last 3 gives us 1. For 96, we can start with 2, which gives us 48. 2 again, which gives us 24. 2 gives us 12, another 2, 6, 2 again, 3, and then 3, 1. So within 54 we can see there is one perfect square, and within 96 we can see there is 1 and 2, so 4 times 4. So we have a perfect square of 16 within the factorization of 96. So we'll go ahead and rewrite as square root of 5 times, instead of square root of 54, we can write the square root of 9 times the square root of 6. And instead of square root of 96, we can write the square root of 16 times the square root of 6. So now we have square root of 5 times 3 radical 6 minus 4 radical 6. So we could distribute the square root of 5 here, but that would be unnecessary because if you notice, these two are like terms, so we can go ahead and subtract them. So we get square root of 5 times -1 radical 6. And when we go ahead and multiply those, we get negative square root of 5 times 6, which is 30. And that's all we can do there. Okay, so we'll treat this next problem very much the same way. We go ahead and distribute the square root of xy into that expression, and we end up with square root of xy times square root of 6x plus square root of xy times the square root of 27y. So we now have the square root of 6x squared y plus the square root of 27xy squared. So we'll go ahead and split each of these into two radicals, the perfect square radical and the non-perfect square radical. So perfect square and non-perfect square. And for the first one, 6 is not hiding any perfect squares in it, so it's going to go into the non-perfect square category. We have x squared, which is a perfect square, that'll go in here, and y will join 6 in the non-perfect square radical. For the next one, we know that 27 has a factor of 9, which is a perfect square. That leaves us 3 for the non-perfect square radical, and y squared is a perfect radical, so it'll go in there. And x is not a perfect square, so it'll join 3. So now we have x radical 6y plus 3y radical 3x. And that's pretty much all we can do for this one. So make sure you can do these before we proceed. So now we have one expression with more than one term times another expression with more than one term. So of course we know how to handle those. If we had just one item, we would just distribute it. If we have two, we're still going to distribute, but we're going to distribute each of these into the next expression. So first we'll go ahead and distribute the 4, then we'll go ahead and distribute the radical 5. It's kind of like sequential distribution. So when we distribute the 4, we get 4 times 3, which is 12, plus 4 times radical 5, which is 4 radical 5, plus, now we're going to distribute radical 5, so 3 times radical 5, we just write 3 radical 5, and then plus radical 5 times radical 5, which is basically radical 5 squared. So 12 doesn't change, plus 4 radical 5 plus 3 radical 5 plus, we know that the square root of 5 squared is just 5. Now we notice we can go ahead and combine the 12 and the 5 because they're like terms, they're just constants which have no radicals in them, so they're just integers, so we get 17. And these two are also like terms because the radical parts are the same, so we can go ahead and combine those and we get 7 radical 5. And that's pretty much all we can do, so we're done with that problem. Okay, so now for this next one, we're going to go ahead and distribute the 3 radical 6 in that way, and then when we're finished, we'll go ahead and distribute the negative 2 radical 2 like that. So when we distribute 3 radical 6, we get 3 radical 6 times radical 2 plus 3 radical 6 times 5 radical 6, Now we're done with that distribution. We're going to go ahead and distribute the -2 radical 2. So we get -2 radical 2 times radical 2. And lastly, we get -10 radical 2 times radical 6. So right here we have 3 radical 12 plus the 3 times 5 gives us 15. And we know that radical 6 times radical 6 just gives us 6. Minus. This 2 will carry. And we know that radical 2 times radical 2 is just 2. And then we have minus 10 radical 12. So if we clean it up, we have 3 radical 12 plus 90 minus 4 minus 10 radical 12. So we can go ahead and combine these radical 12 terms to get -7 radical 12 plus, we can also combine those two constants to get AD6. So the last thing we'll want to do is make sure this is simple, and of course we know that 12 breaks down into 2, 6, 2, 3, 3, 1. So we can break it up as square root of this perfect square, which is 4 times the square root of 3 plus 86. So we end up with -7 times 2 radical 3 plus 86. And that's going to give us -14 radical 3 plus 86. And that's pretty much all we can do there. For the last one on this page, we're going to be distributing the square root of 6p into the next set, and also when we're finished we'll go ahead and distribute the -2 radical q. So when we do so, we end up with 8 radical 6p radical q plus 5 radical 6p times radical 6p. Then now we're ready to distribute the negative radical q, so we end up with -16 radical q radical q, and finally -10 radical q radical 6p. So now we'll clean this up. We notice that we have 8 radical 6pq plus 5. Now we know that radical 6p times radical 6p is just going to be 6p. That's basically using the rule that says square root of x squared equals x. So we get times 6p minus 16. Same thing happens with these two radical q's. When you multiply them, you just get q, and then minus 10 radical 6pq. All right, so continuing with the cleanup, we have 8 radical 6pq plus 30p minus 16q minus 10 radical 6pq. So we do notice that these two terms are like terms, so we can go ahead and combine them. So let me go ahead and start up by writing 30p minus 16q, and then we have minus 2 of those, so minus 2 radical 6pq. All right, so here's a few more problems for you to make sure you understand before we proceed. Okay, let's try these square expressions now. And even though we can write these out twice and just multiply them like we did with the previous 3 problems, it is much more efficient if you recall this rule from the past, which was the square of a binomial rule. So when we had f minus l squared, we know we get f squared minus 2fl plus l squared, and we had one for some case as well. The square of a sum like that was f squared plus 2fl plus l squared. The positive case is all positive, since most students tend to have difficulty with negative signs. I went ahead and chose some negative examples, subtraction cases. So in this case, in the first example, we can see that what plays the role of f is going to be square root of 3 and at 13, that is, and what is playing the role of l is the square root of 5. So we go ahead and apply this rule. So first one squared minus 2 times the first times the last plus the last one squared to this f and this l. So we end up with square root of 13 squared minus 2 times f, which is square root of 13, times l, which is square root of 5, and then plus the l squared, which is going to be square root of 5 squared. Now we know that square root of 13 squared is just 13 minus 2. I notice there's no perfect square within 13's factorization nor within 5's, so I can go ahead and multiply those. So I get minus square root of 65, and I know for sure that's simple because there were no perfect squares in either one of those radicands, plus square root of 5 squared, which is 5. Now we notice we can go ahead and combine these two integers to get 18 minus 2 radical 65, and that's pretty much all that can be done. We're going to do the same thing with this. Makes no difference that they both have radicals in them. So here our f will be square root of 6 and our l will be 4 radical 2, and we're applying this formula again. So we get f squared, which is going to be square root of 6 squared, minus 2 times f, which is square root of 6, times l, which is 4 radical 2, plus l squared. So that's going to be 4 radical 2 squared. And make sure that you use parentheses around that because both those factors need to be squared. So we get square root of 6 squared is just 6 minus no perfect square inside 6 or 2. We can go ahead and multiply those, and the 2 and the 4 can be multiplied as well to give us 8 radical 12 plus (16) times square root of 2 squared, which is 2. Now this time we can go ahead and simplify the square root of 12 first. So we end up with 6 minus 8. We know there's a 4 inside the factorization of 12, which is a perfect square, so we can separate those in that way, and then we get plus 32. So these two, of course, are just integers. They can be combined, so we get 38 minus 8 times 2, which is 16 radical 3, and that's fully simplified now. Notice that when we said here that we can go ahead and multiply those knowing we're not going to get a perfect square in here, it's because they also didn't have any shared factors. They don't have any factors in common that could have been multiplied to end up giving us a perfect square, as was the case here. Yes, this is not a perfect square and that's not a perfect square, but they share a common factor of 2. So that's why we have to be careful when we make that assumption, so that when there is a new perfect square that comes, notice that was the 2 from here and that 2 that gave us the perfect square 4. So be careful with that. Don't assume just because these two are not perfect squares that their product won't have a perfect square factor in it. All right. So moving on to the next case with the variables, the same exact rule applies, with f being square root of x and L being the square root of y. So now we start with f squared, so that's going to be the square root of x squared minus 2 times f, which is square root of x, times L, which is square root of y, plus L squared, which is going to be square root of y squared. So now we're just going to clean it up. So we have x minus 2 square root of x y plus y. And there's no more combining that's possible, so we are finished. Again, please make sure you understand and are able to do these on your own before we proceed. Let's go ahead and try a few more of these before we move on. So in this particular case, we notice that we have a special formula that applies in these. You should recognize these two expressions as related, because notice they have the exact same terms in them. The difference is the operation involved between the two terms. And whenever we have expressions like that, those are called conjugates. If you remember, we had a rule for multiplying conjugates, which went like this. When you have f plus L times f minus L, that actually just ends up being the difference of their squares, f squared minus L squared. So in the first example, we noticed that what's playing the role of f is 6, and what is playing the role of L is the square root of t. So basically, we're going to get f squared, which is 6 squared, minus square root of t squared. Basically, the attitude to have toward math is it's like a game that you can play. Just there are rules, you apply them, and that's as simple as that. They just happen to be rules that may someday provide a livelihood. That's the difference. So rather than just playing games, which can be fun, and that's good too. All right, so we get 6 squared, which is 36, minus square root of t squared, which is t. And that's it. There's no more combining that's possible, so we'll leave it at that. All right. So in the second example, we also notice that we have the f plus L times L, f minus L scenario. So once again, of course, we can apply the same rule with f being played by the square root of a, and the role of L being played by 6 radical b. So we get f squared, so that's going to be square root of a squared minus L squared, which is going to be 6 radical b squared. So the square root of a squared we know is just a minus, now in this group we have to square each of those factors, so we get 6 squared, which is 36, and square root of b squared, which is going to be b. No more like terms, so we are finished. We notice once again in the next example we do have the right form. So the role of f is being played by the cube root of 2. The role of L is being played by 4. So we do get f squared. Now be very careful with this one. Minus L squared, which is going to be 4 squared. Now the cube root of 2 squared, as you know, is not 2 because it's not the square root of 2 that's being squared. So that's basically, if you think about it, that's just the cube root of, if we had a nice rule from the past, let me remind you, when you have the nth root of x to the m, that's actually the same as the nth root of x to the m. And both of them are actually equal to x to the m over n. We're not really dealing with this part right now, but we're using this fact right now. So we get the cube root of 2 squared, which is 4 minus 16. And of course, there's nothing else that can be done here, so we are done. And that's how you multiply and simplify when there's more than one term involved. Of course, even if, say, one of these expressions had 10 terms, doesn't make any difference. Let's say the second expression had 10 terms in it. Then you just go ahead and distribute the first item here by all those terms, then the second one by all those terms, then you combine like terms. So the procedure can be generalized with no problem. Next, we want to look at the concept called rationalizing the denominator of a fraction, and what that basically means is just making sure there are no radicals left in the denominator. So all of these are possible to rationalize the denominator of, and the way we can do that is by remembering the fact that if you have the square root of a number like x and you multiply it by the same square root, you just end up with x. This is what's going to help us simplify these. So basically, you write your problem and you're going to multiply by a clever fraction, which is going to rationalize that denominator. In this case, just the square root of 2, because I know if I multiply square root of 2 by square root of 2, that's just going to become 2, which is a rational number. Of course, I can't just multiply the denominator of a fraction by a number, whatever that is. I have to multiply it on the top as well. So I do that, and now we end up with 8 radical 2 over square root of 2 times square root of 2, which is just 2. And notice, now we can go ahead and simplify the 8 and the 2 to leave us 4 on the top and 1 here. So we just end up with 4 radical 2. And that's how we rationalize these denominators. Definitely try the next couple on your own before you come back. So when we want to rationalize something like this expression, we always look to see if what the radicand is is possibly reducible, meaning is there a perfect square hidden inside it or not? If there is, we'll want to simplify it first before we rationalize, because then we'll need a much smaller square root to rationalize. Notice neither 2 is hiding a square root, a perfect square in it, nor 10. So we go ahead and proceed just as before. We're going to multiply by square root of 10 down here, which means we have to multiply by square root of 10 on the top as well. So when we do so, we end up with 45 radical 10 over 10. And as always, we will simplify before we call it quits. We notice that 5 goes into both 45 and 10. It goes into 45 9 times, and it goes into 10 2 times. So now we clean it up and we just write it as 9 radical 10 over 2. And that's pretty much all we can do. Now this next one, we have 15 over square root of 75. I do notice that if I look at the prime factorization of 75, I start with 3 because 7 plus 5 is 12, which is divisible by 3. When a number ends in 5, you always want to try 3 before you move on to 5. So we get 25, and then I know 5 goes into that 5 times, and again 5 will give me 1. So now on the left side you can see the prime factorization of 75. So in fact there is a perfect square hidden inside there. So I'll go ahead and do that first. I will reduce this like this. I'll break up 75 as the square root of 25 times the square root of 3. So now we end up with 15 over 5 radical 3, which is nice because now all I need to rationalize the denominator is just to multiply by radical 3, which of course I need to do on the top as well. Notice it wouldn't have been wrong if you multiplied top and bottom by the square root of 75. It's just that you would need to deal with larger numbers, and then at the end you would have to simplify that anyway. So it's better always to simplify first and deal with smaller numbers rather than wait and do it at the end. So just so you know, it would have been okay to do that. All right, so now we're gonna go ahead and reduce this. So that leaves me 1 here and 3 on the top. And now we have 3 radical 3 over, remember that square root of 3 times square root of 3 is 3. So now we notice that those will cancel out, and we end up with the final answer of just square root of 3. So again, of course, make sure you understand these before we continue. Okay, I wanted to look at a few more of these before we proceed. So again, we notice that square root of 27 here is reducible, so we can go ahead and write the square root of 27 as the square root of 9 times the square root of 3. So we get 6 times the square root of 8 over 3 radical 3. Now we're going to need a square root of 3 to rationalize on both the top and the bottom. So we end up with, let's go ahead and do this to make matters simpler. So we get 2 radical 24 over 3. Now we realize 24 also, notice you have 2, 12, 2, 6, 2, 3, 3, 1. So there is a perfect square inside it. So we can write the square root of 24 as the square root of 4 times the square root of 6 over 3 like that. So now 2 times square root of 4 is just 2. 2 times 2 is 4. So we get 4 radical 6 over 3. And now there's nothing else we can do, so we are finished with that. Moving on to the next problem. It's probably a little bit easier if we go ahead and bring those under one radical first. And the reason that we would want to do that is so that we can take care of any possible cross-canceling first. Now we notice that, for example, 20 and 15 have a common factor of 5, which goes into 20 4 times and into 15 3 times. Now we also notice that 21 and 14 have a common factor of 7, which goes into 21 3 times and into 14 twice. Now you notice there's no more cross-canceling possible, but notice how much nicer and smaller our numbers have become. So now we have basically the square root of 8 over 9, which if you break up as the square root of 8 over the square root of 9, that takes care of the rationalizing of the denominator already. That's just 3. And of course, square root of 8 we know is there's a perfect square of 4 hidden inside 8. So we can break the square root of 8 like that, and we end up with 2 radical 2 over 3. And that's all we can do there. So you see, there's not just one way of doing these. I usually like to recommend to you the most efficient way, but you may have done something else and ended up with the correct answer, and that's okay too, no problem. Sometimes, you know, instead of taking the shortest route when you're going from work to home, you may take a longer route, but you're still gonna get home, so no problem with that. All right, for the next one, of course, we'll go ahead and break it up before we rationalize the denominator. And just because there's a variable doesn't change the nature of the problem. We're still going to rationalize. And notice what we need to rationalize the square root of y is the square root of y again. So don't forget to do the same on the top. And now we're going to end up with the square root of x, y on the top. And downstairs, square root of y times square root of y, as you know, is just y, and that should do it for that one. Again, really simple but very important, and you'll be using all of these in pretty much every math class that you take from here on, so you'll want to be very, very comfortable with these concepts. So make sure you can do them on your own, and then we'll move to the next screen. Let's look at a couple of more examples with variables in them, and then let's look at one which has a cube root in it before we consider this topic understood. Okay, so for the first one, we'll just go ahead and break it up. So we get square root of 49t to the 5 over the square root of 2u. We're just using the quotient rule for radicals to break that up. And we notice that in order to rationalize, we're going to need to multiply by the square root of 2u. And we don't forget that we need to do that on the top as well. So now we have the square root of 49t to the 5 times 2u on the top, and downstairs we have just 2u. So we will break up the top radical into 2 radicals. We'll put all the perfect squares in the left radical and whatever is left in the right radical. So We know 49 is a perfect square. It can go there. In 2 to the, as far as t to the 5 is concerned, notice that's t times t times t times t times t. So you can see this much of it is a perfect square. So t to the 4 will go in here, and t will go here. Don't forget that we already had a 2. Let me start with that. Let's go ahead and put the 2 in there first. So we have a 2 there already, and then a t. And notice that u is also not a perfect square, so that's going to stay under the radical in the next radical there. And that should account for everything. Make sure everything is accounted for. The 49 is accounted for, 2 is accounted for, t to the 5, t to the 4 of it went in here, and t is there, so it's accounted for, so we should be in good shape. Downstairs we just have 2u again, and now we end up with the square root of 49 is 7. The square root of t to the 4 is t squared. Square root of 2tu over 2u. And that should do it for that problem. We just have to make sure no radicals are left in the denominator, and that no perfect squares are left in the radical on the top, and we should be fine. Okay, so for this next problem, we're going to go ahead and split it up as well, but it's a good idea in a situation like this where the numerator and the denominator seem to have common factors that can be reduced first, that you do the reduction first before you split it up, because once you split it up, you can't reduce it as simply. So let's do that first. We notice that 8 and 24 have a common factor of 8, so that cancels, and we get a 3 down here. Notice all of this is still going to be under the radical, so u to the 5 and u to the 6, we know have a common factor of u to the 5, and it goes into the u to the 6 u times, and we know we can cross cancel v and v cubed, leaving us a v squared on the top. So now we have a much nicer, simpler expression that we're dealing with. So now we have the square root of, notice on the top, the only thing that's left is v squared. And notice that downstairs, all that's left is 3u. So now if we break it up, see how much simpler that is? We end up with the square root of v squared over the square root of 3u, which we will go ahead and rationalize now by just multiplying by the square root of 3u, and make sure you do the same on the top. So the square root of v squared is a simple, nice v. So we get v radical 3u over 3u. And that's all that we have to do for that problem. All right. So one more problem here. That one involves a cube root. And we're going to go ahead and split it up. So we get the cube root of 8 over the cube root of 9, and the cube root of 8 is a simple 2. Now notice that to rationalize a cube root, we're not going to want to get a perfect square here. We're going to want to get a perfect cube. So when we look at the prime factorization of 9, we see 3, 3, 3, 1. So we ask ourselves, what's missing from this factorization where we have 2 3's in the factorization to get to a perfect cube? See, the fastest way to get to a perfect cube is just to multiply by a 3. So here we're going to write the cube root of 9, and to go ahead and simplify that, we're going to put cube root of 3. That's all we need, because now notice under the radical, once we multiply, we get 9 times 3, which is 27. And that's how you handle those. So, and on the top, we have to multiply the exact same thing like that. So for our final answer, we're going to write 2 times the cube root of 3 over, well, let me do one more additional step, over the cube root of 27, which as we now know is just 2 times the cube root of 3 over 3. And that pretty much does it for that problem. So notice you have a cube root, which is going to require a slightly different kind of handling. In order to rationalize a cube root, you have to make sure you get to a perfect cube. Okay, I think we should look at one more of these cube roots before we go on. Notice this one in the middle that I just added. So if we go ahead and split that up, we get the cube root of x over the cube root of 2y squared. So remember, we're going to multiply by some expression, some cube root. So I know it's going to be a cube root. And what my goal is to take this 2y squared and turn it into a perfect cube. So we have 2y squared, we want to make it a perfect cube. Notice what's missing from 2 is going to be 2 factors of 2. So which is what? Which is 4. So we're going to need a 4. We're going to multiply by a 4. Let me write it like this. So we're going to have to multiply by a 4 to turn the 2 into a perfect cube, which is basically 8. And what's missing from y squared to make it a perfect cube? Notice just a single y. So we're going to multiply by y, and now when we multiply, we get 8y cubed. So that's where we're headed. So that's why what we need to multiply under the cube root here is going to be 4y. So of course we have to do the same on the top. Notice how it works out nicely now. We get the cube root of 4xy on the top. On the bottom, we now have the cube root of 8y cubed, which is a nice perfect cube. So we end up with the cube root of 4xy over 2y. And that can now be considered simple because there is no radical in the denominator and there is no perfect cube left under the radical on the top. So that we consider to be the simplified answer. So these are not difficult, but they need a little bit of getting used to. So make sure you practice these before you continue. Okay, so now we're looking at more rationalizing the denominator problems. And this time, we don't have just a single radical in the denominator. We have 2 terms. So that's going to require that we remember a rule we discussed earlier, which was, if you remember, when you have f plus L times f minus L, that ends up yielding f squared minus L squared. And these are called conjugates. And that's precisely what we're going to need here to help us simplify these. So if I write 5 over 4 minus radical 3 and multiply not just by radical 3, but by the conjugate of 4 minus radical 3, which is namely 4 plus radical 3, that's how I will completely get rid of the radical down there. Because notice, let's just take a quick look down here. Notice if I just multiplied 4 minus radical 3 by a radical 3, right? Then I would end up with 4 radical 3 minus 3. Yes, I rationalized this radical 3, but I created a new problem, another radical. So this is why we don't want to take this approach of just multiplying by the radical. Now this, on the other hand, notice how nicely that will work out, because now we will get, we'll get 5 times 4 plus radical 3 on the top. Down here, remember, your f is going to be 4 and your L is going to be square root of 3. So you're going to get f squared, which is 4 squared, minus L squared, which is square root of 3 squared. See now, that's not a radical. And here, once you square that, you get 3. So the radicals are completely gone. So we end up with 5 times 4 plus square root of 3 over 16 minus 3. So that's 5 times 4 plus radical 3 over 13. Notice I didn't multiply the 5 in until now, because I wanted to make sure I don't end up with something down here which can be simplified with that or cross-canceled with that. Now that I know for sure it doesn't exist, I'll go ahead and distribute the 5, and we get 20 plus 5 radical. My pen is not cooperating tonight. Sometimes doesn't write what I want it to write, but such is life, right? Bigger problems than this exist, so we're not gonna fuss over it. So, and then we have 13 down below, and now we have our simplified answer right there. Okay, so the procedure is not difficult, but different. So you have to make sure that when you have more than one term like this, you handle it by multiplying not by itself, notice, but by the conjugate, because it's a product of conjugates that gives us a difference of squares. Go ahead and try the next one before you come back to see the results. Welcome back if you did what's good for you. So we get 9 plus square root of 7 over 5 minus square root of 7. And remember, we're going to multiply both the numerator and denominator by the conjugate of the denominator. So we get 5 plus square root of 7, 5 plus square root of 7, like that. And now we're going to go ahead and write the top as a multiplication like this. 9 plus square root of 7 times 5 plus square root of 7 over 5 squared, which is 25, minus square root of 7 squared, which is 7. All right. So as far as this multiplication here is concerned, you can just do it horizontally, or you may want to try this. I like these boxes. So we can put 9 plus square root of 7 like that, and we can put 5 plus square root of 7 like that. Then you can multiply it like a times table. See, 9 times 5 gives us what? 45. And 9 times radical 7 just gives us positive 9 radical 7. Positive radical. Now we're just going to move on to this, multiply this by this. So just like a times table. So we get plus 5 radical 7. And then these two multiply to give us just 7. And we notice that the nice thing about doing it using this table is that the like terms kind of line up like that nicely. So 45 and 7 are like terms. So we have two groups of like terms. One is here in the green and the other one in the red. So we end up with 52 plus, that's just from 45 plus 7, and 9 and 5 is 14. So plus 14 radical 7 over 25 minus 7, and 7 from 15 is 8, so 18. Now we don't want to leave it like that, because I notice that here we have a common factor of 2 that can be factored out, so we'll do that. That leaves us 26 plus 7 radical 7 over 18. And it's a good thing that we cut that, because now we can reduce these to 1 and 9, and we can finally write our final answer, which is going to be 26 plus 7 radical 7 over 9. And then we can box it, because there's nothing else we can do. All right, so that's a nice problem. Make sure you understand it. Okay, so now let's go ahead and take care of this last one on the right with the variables in it. And of course, we handle it in exactly the same way. So we're going to go ahead and multiply the numerator and the denominator by the conjugate of the denominator, which of course, as you know, is the square root of x plus the square root of y. And of course, don't forget to do the same on the top. So what we end up with now is the square root of x plus the square root of y times the square root of x plus the square root of y over, as you know, this is a product of two conjugates, with f being the square root of x and L being the square root of y. So we get the square root of x squared minus the square root of y squared. Now on the top, we notice that's the square root of x plus the square root of y squared. Downstairs we have x minus y, because the square root of x squared is just x, the square root of y squared is just y. Now for this, we can of course use our f plus L squared rule, which is f squared plus 2fl plus L squared. So we get the first one squared. Square root of x squared is just x, plus 2 times square root of x times the square root of y, that's 2fl, plus L squared, which is just y. And we get over x minus y. So finally we end up with x plus 2 radical xy plus y over x minus y. And that is all that can be done here. So the same exact methodology, just variables involved, no different from the previous ones. Make sure you can fully repeat these on your own without any help before we go to our last screen, believe it or not. We're almost done, so hang in there. Okay, so I just wanted to take a look at this couple of problems here, because what happens with these, a lot of times students do some illegal cancellations to simplify these, and I want to make sure that you avoid doing that. because we have two terms here, of course, we can't cross cancel. So that doesn't mean there is nothing we can do, because if you notice on the top, we do have a common factor of 3. So the proper way of doing these is to go ahead and use factoring. So 3 leaves us 4 plus 7 radical 2 over 15. And now we can legally cross cancel these because they are now factors. That leaves us 5 and 1 on the top. So we just basically end up with 4 plus 7 radical 2 over 5. Okay, so on the next one, basically we do the same thing, except we should go ahead and simplify the square root of 800. And the square root of 800, as you know, is hiding some perfect squares under it. So in fact, notice that the square root of 800 is, you can see the biggest perfect square inside there is the square root of 400, and that leaves us the square root of 2. So it's basically 20 radical 2. Or if you aren't that comfortable with numbers to realize that, you can of course always do the prime factorization of 800, which gives us 2, 400, 2, 200, 2, 100, 250, 225, 5, 5, and finally 5, 1. So we can see there's a perfect square, there's another one, and there's another one. So that's 25 times 4, which is 100, times another 4, which is 400. So the perfect square part of or factor of 800 is 400. We should say the largest perfect square factor of 800 is 400, and then it leaves us 2. So that's where we got the 402. So in case you can't just do that in your head, you can always do the longer process of prime factorization and get to the same result. So no worries. All right, so we're gonna go ahead and write this as negative 24 minus the square root of 400 times the square root of 2 over 4. Now we know that that's going to be negative 24 minus 20, of course, because 20 squared gives us 400. So the square root of 400 is 20 radical 2 over 4. And we do notice that we have a common factor of 4 here between these two terms. So we can take that out. And that leaves us negative 6 minus 5 radical 2 over 4. Now we can legally cancel those 4's and be left with negative 6 minus 5 radical 2 for the final answer. All right, so that's how you tackle simplifying these radical expressions, and that should do it for today. So be safe until we meet again.